So here's an example of an integral where you would want to use trigonometric substitution. I'm going to fix this microphone. So the times when you use what we call trig substitution, which I'm going to introduce in this video, is when you're stuck integrating a square root of a sum or a difference. When you have addition or subtraction under a radical like this, this is when you should consider trigonometric substitution. The reason is, this is certainly not true. It's not as simple as square root of 1 plus the square root of x squared. That's one of those math felonies. That's very naughty if you do that. And I'm standing in front of it, sorry. So you cannot distribute a radical over addition or subtraction. It violates order of operations. So that's not going to work. I lost my eraser. A regular substitution is not going to work. If we let u equal 1 plus x squared, then du would be 2x dx. So the multiple, I'm going to stand where you can see me. The multiple of 2 is no problem, right? Multiply by 2, multiply by 1/2 outside. You've seen me do that in a lot of other videos. The multiple of x, though, the fact that we need 2x dx, you can't just multiply by x here and put 1 over x outside, because you can't move expressions of x outside of the integral. And if you multiply by x on the top and bottom, well, then you're no better off. If the x has to stay in the integral, you're still not going to be able to evaluate. So trig substitution saves us here. And I guess with this example, let me just give you the substitution. So in future videos, I will talk about how we're supposed to figure out what trig function to replace x with. But in this case, since this is an introductory video here, I just want to show you the usefulness. So the idea with trigonometric substitution is we replace x, and I should put a let in front of this, because this is certainly not something we would assume to be true. Suppose we let x equal tangent of theta. So we're going to replace x with the trig function tangent of theta. The idea is you can actually let x equal whatever you want. Ideally, you want whatever the values of x that are allowed in the domain of this integrand, we would want to be able to generate the same values with the function that's replacing it. In this case here, x can be any number, because when you square it, it's going to be something positive plus 1. You'll have a positive number under the radical. So the domain here is all real numbers. X could be any real number. If you recall, the range of tangent graph looks like this. Tangent also takes on all real values. So that's one thing you want to be careful about. It's kind of happening in the background. But because this comes out of nowhere, just so you believe me that this is legitimate, here x can be any real number, here tangent theta can be any real number. So this substitution is legitimate here. Okay, and I might be getting a little too into the details with that, but so the plan is to replace x with tangent of theta. One thing you have to be careful of, though, or a couple of things you should be careful of when you set up your trig substitution. One thing, make sure you use a different variable here. Don't write x equals tangent of x, because that's not true. Right, in general, you can't, x is not equal to tangent of itself. So you need to use a different variable here. If you don't like drawing thetas, that's fine. Make it u or t or whatever. But use some other variable here. Don't write x equals tangent of x, because that's nonsense. Also, as soon as you set up your substitution here, you need to consider, so if you're going to replace x with tangent theta, then you're going to need to also translate dx to something in terms of theta. So the derivative here, so again, you need to really memorize those derivatives of the trig functions. Derivative of tangent is secant squared theta times d theta here. Okay, so plug that into the integral. So instead of the integral of 1 over the square root of 1 plus x squared times dx, now we're going to integrate 1 over the square root of 1 plus, so instead of x squared, we're going to put tangent squared, and instead of dx, we're going to put secant squared theta d theta. So this is replacing dx. This is replacing x. So how does that help? Well, if you remember your trig identities, 1 plus tangent squared in the denominator here is equal to secant squared theta. So this is equal to 1 over the square root of 1 plus tangent squared is equal to secant squared. And then times, we have secant squared theta here. Okay, so the square root of secant squared, trying to decide how I want to line this up, is, so I'm going to write it as just secant theta. I'm making a bit of a jump there, and I'll come back and defend it in just a second. But so square root of secant squared, secant theta, times secant squared theta here, d theta. So now the secants cancel, and we're just integrating secant to the first. Okay, and I'll move on with that in a minute, but let me point out a couple of things. So the advantage of trig substitution is when you have a sum or a difference that you're stuck with, that's kind of locking up your ability to integrate an expression like this. The idea is to take advantage of these trigonometric identities. So this is one of them. Another one that you will use with trig substitution is 1 minus sine squared theta is equal to cosine squared theta. And another one is secant squared theta minus 1 equals tangent squared. But what's common to these equations is you take a sum or difference and you turn it into a single perfect square. So in this case, when we replaced x with tangent theta, the 1 plus tangent squared now boiled down to a single perfect square, and then we could take the square root and then we just move on with our lives with integrating. So that's the hope with your trigonometric substitution, is you're supposed to identify, well, what trig identity does this expression remind me of? And then you insert a trig function in place of the x so that hopefully it'll simplify using one of these Pythagorean identities so that you can take care of the square root. Because when there's a sum under there, we're kind of stuck with that square root. So we're trying to get rid of the square root, is the idea with these trig substitutions. Okay, one other thing. So when I do this, the square root of secant squared theta is equal to secant theta. When I write that, I'm assuming that secant theta is positive. And I want to defend that. Okay, this is going to be a bit of a tangent here. Pun intended. But when we do this substitution, x equals tangent theta, we should put a little condition on here that we're only allowing theta to range from negative pi over 2 to pi over 2. And this should be a strict inequality because tangent's undefined at negative pi over 2 and pi over 2. That's where those vertical asymptotes are in the graph. The reason we should restrict the range of theta here is so that when we untangle this and write it back in terms of x, it's a little easier. Also to make it easier to simplify, like at this stage here. Because if we restrict theta to be between negative pi over 2 and pi over 2, and notice how this restriction right here is the same restriction we used with the inverse tangent function, and that's always going to be the case. So if you would do x equals, say, sine theta, then we would use this same interval, because that's the interval we use with inverse sine. I'm not going to hold you guys to writing that down. If you don't write this condition here, I'm okay with it. And if you just say square root of secant squared is equal to secant, I'm okay with it. You don't have to defend it. That's always going to be the case when we do these trig substitutions. But I just want to explain to you why it's okay. So if theta is between negative pi over 2 and positive pi over 2, that's between here and here. So theta is somewhere in this range in terms of, picturing unit circle. Then cosine is positive in either one of those quadrants. Cosine is associated with the x-coordinate. X-coordinate's positive in both quadrant 1 and quadrant 4. 1 over cosine, so secant would also be positive then. So it's a fair assumption that secant theta is positive. And so it's fair to say square root of secant squared is equal to secant theta. Okay. So that's my reasoning behind that. So now, like I said, along the way with this integration, now we're just integrating secant theta. So I've said this in a previous video. Once you get down, and it's right on top of the glare again. Once you get down to the integral of just a single trigonometric function like this, then either you have the antiderivative memorized, which is ideal, or you look it up. So in a case like this, this is another case where you may not have this antiderivative memorized, and that's okay. So you just look it up, natural log of absolute value of secant theta plus tangent theta plus c. Okay. So we've got an antiderivative. That's good, but the catch is it's written in terms of theta, and our original problem is in terms of x. So we need to write our answer in terms of x. So we still need to convert this back to x. And I don't want to try to squeeze that into the bottom of the board like I tend to do sometimes. So let me come up here. I want to keep the information about what we let x equal. Okay. So we worked on this integral, we applied this substitution, we got this antiderivative, natural log of secant theta plus tangent theta plus c. We want to write, now we need to write our answer in terms of x. That's what I'm trying to do right now. Okay, well, tangent theta is x. So that part's easy enough. We can replace this tangent theta right here, just call it x. Okay. So if I'm writing out the overall solution here, it's natural log absolute value of, so we need something in place of the secant theta here. We need to write secant theta, right? Secant theta in terms of x. X, which is equal to tangent theta. Okay. So we've got natural log of secant theta plus tangent theta, which is equal to x. So we're done. We've converted that part of this expression anyway, plus c. So this is going to be our final answer as soon as we can fill in this blank. Okay, oops, let me get rid of this. So in this case, we know that x is tangent theta. We want an expression for secant theta. There's a trig identity that relates those. So I would just use that. I would use the fact that 1 plus tangent squared theta is equal to secant squared theta, right? Because we're looking for an expression for secant. Okay, well, tangent theta is equal to x. So 1 plus x squared is equal to secant squared theta. And again, because we're confident that secant theta is positive, we could just take the square root of both sides here, and we know that this is equal to secant theta. So secant theta is equal to this, the square root of 1 plus x squared. And once we fill in the blank there, then that's our final answer. Now, I'll say, I realize this is a long, fairly complicated process, and this is even a more straightforward problem compared to some other ones you might solve. It'll get quicker once I was explaining in detail every step of the process, but it's still going to take a long time every time you do a trig substitution. So it is a method of kind of last resort. I mean, you want to consider, can I do a straight u substitution? Can I integrate by parts? But in general, when you find yourself integrating, you have a sum or a difference, addition or subtraction under a square root like this, and you can't get a regular u substitution to work, then you're probably going to want to use a trig substitution.